Hello friends, continuing with the chapter of semiconductor and electronic devices. Today we come to its second part, semiconductors itself. What is today's topic? Today's topic is semiconductors. Previously we have studied about formation of energy bands in solids, and now we come to the main topic, semiconductors. Now some properties of semiconductors let us recall. First, definition. Semiconductors partially allows electricity to pass through it. I repeat, semiconductors partially allows electricity to pass through it. Examples are carbon, silicon, germanium, stannous and plumbum, the fourth group elements of periodic table. Third, outermost orbit possess 4 electrons. Fourth, Ohm's law. Do not obey Ohm's law. Semiconductors do not obey Ohm's law. Resistivity. Resistivity varies between 10 raised to power minus 8 to 10 raised to power minus 12 ohm meter. Resistivity varies with temperature, as rho T is equal to rho 0 into e raised to power Eg by kBt. Conductivity varies with temperature, as sigma T is equal to sigma 0 into e raised to power minus Eg by kBt. Number density varies with temperature, as Nt is equal to N0 into e raised to power minus Eg by kBt. Energy band diagram is as shown in. Energy gap between valence band and conduction band is of the order of 1 electron volt, and type of bonding is covalent bonding. Semiconductors enter covalent bonds. So these are some of the properties of semiconductors that we have recalled. Now we will take up some of them in more details. Now, covalent bonds in semiconductors. Let us try to understand how covalent bonds are formed. They are formed due to mutual sharing of electrons between atoms. I repeat, mutual sharing of electrons takes place between atoms during formation of covalent bonds. Now look at this diagram. Here we have shown silicon. Silicon has 4 electrons in outermost orbit. Now here we have shown 5 silicon atoms, each having 4 electrons in their outermost orbit. Now they share electrons. Here these 2 electrons are shared by silicon and the central silicon. Similarly, the other silicon atoms, this also shares 2 electrons. This silicon also shares 2 electrons. Now this silicon also shares these 2 electrons, and they form covalent bonds. Similarly, here we have shown germanium. This is central germanium atom which shares electrons mutually with other germanium atoms, this and this, and becomes stable. So central germanium becomes stable by mutual sharing of electrons. So therefore they form covalent bonds. So silicon, germanium form covalent bonds. Even other fourth group elements also enter covalent bonding. Those elements which have whose atoms have 4 electrons in their outermost orbit enter covalent bonding. Now assignment 14 continues. Question number 8. Give any two examples of semiconductors. Question number 9. Write the expression for resistivity and number density of electrons in terms of energy gap between valence band and conduction band. Now thermal agitation in semiconductors. What is thermal agitation? The process by virtue of which bonds break up even at room temperature. Electrons leave their atoms and become free, leaving behind a hole in crystal lattice. I repeat, the process by virtue of which bonds break up even at room temperature. Electrons leave their places in the atom and become free, leaving behind a hole in crystal lattice. Pure semiconductor behaves as an insulator at 0 Kelvin or minus 273.16 degree Celsius. Now look at this diagram. This is energy band diagram at 0 Kelvin of a semiconductor, where valence band contains 4 electrons and conduction band is free of electrons. So it behaves as insulator at 0 Kelvin. Why insulator? Because conduction band contains no electrons. It is empty. Now here you look at this diagram. This is a central germanium. It shares 4 electrons mutually with other germanium atoms and becomes stable. So this is how semiconductors behave as insulator at 0 Kelvin, because there are no free electrons in the lattice which can carry the current. Okay. Now look at this diagram. This is energy band diagram of a semiconductor at more than 0 Kelvin. Here conduction band contains 2 electrons which have come from valence band. Now how they have come to conduction band? Let us see. Covalent bonds break up at temperature more than 0 Kelvin and electrons become free, leaving behind a hole in crystal lattice. The semiconductor possesses 2 types of charge carriers, electrons as well as holes. The number density of current carriers, electrons or holes, is given by the expression Nt is equal to N0 into e raised to power minus Eg by kBt. I repeat, covalent bonds break up and electrons become free, leaving behind a hole in crystal lattice. The semiconductor possesses 2 types of charge carriers, electrons as well as holes. The number density of current carriers, electrons or holes, is given by the expression Nt is equal to N0 into e raised to power minus Eg by kBt. Now you here look at this diagram of germanium which had entered covalent bonds. Now here this bond breaks up. The electron leaves its place, leaving behind a hole in crystal lattice. Similarly, when this bond breaks up, the electron leaves their place in crystal lattice and leaving behind a hole in crystal lattice. These covalent bonds break up due to high temperature. When temperature rises beyond 0 Kelvin, then covalent bonds start breaking. Now at 0 Kelvin, a pure semiconductor behaves as an insulator. Now when temperature rises beyond 0 Kelvin, then covalent bonds start breaking. So number density of charge carriers, that is electrons and holes available depends upon temperature and is given by the expression Nt equal to N0 into e raised to power minus Eg by kBt. Now conductivity of semiconductors. Whenever a covalent bond break up due to thermal agitation, an electron and hole pair is generated in the lattice and they move in opposite direction. Thus, current is carried by both holes as well as electrons. Number density of electrons Ne is equal to number density of holes Nh in pure semiconductor. Ne is equal to Nh and conductivity sigma is equal to Ne into E into mu E plus Nh into E into mu H, where Ne is number density of electrons, mu E is mobility of electrons, and Nh is number density of holes, mu H is mobility of holes, and E is charge on electron or hole. Now look at this diagram of germanium lattice. Suppose this bond breaks up, an electron becomes free and a hole is created in the lattice. Now electron from this pair moves and fills this hole and a hole is created in this covalent bond. Similarly, an electron from here will fill this hole and a hole is created here, and this way the process goes on, so thus they move in opposite direction. Now type of semiconductors. There are two types of semiconductors. Number one, intrinsic semiconductors, which are pure without impurity, and number two, extrinsic semiconductor, which are impure and are with some impurity elements. Now we take up one by one. First we take up intrinsic semiconductor. So first definition of intrinsic semiconductor. Semiconductor in its purest form is known as intrinsic semiconductor. Now what are properties of intrinsic semiconductor? Number one, number density of electrons is equal to number density of holes, that is Ne is equal to Nh is equal to Ni. Ni for intrinsic, number density of intrinsic semiconductor. Second, Ne into Nh is equal to Ni square. Third, conductivity is sigma I, I for intrinsic. Sigma I is equal to Ne E mu E plus Nh E mu H. But Ne is equal to Nh is equal to Ni in intrinsic semiconductor. Therefore, sigma I can be written as Ni into E into mu E plus Ni into E into mu H, or we can take out common Ni into E common within bracket mu E plus mu H. The sigma I is equal to Ni into E into mu E plus mu H within bracket. Okay, so this is how we have the expression for conductivity of intrinsic semiconductors. Number 4, conductivity of intrinsic semiconductor can be increased by adding foreign impurity elements. I repeat, conductivity of intrinsic semiconductor can be increased by adding foreign impurity elements. Now second, extrinsic semiconductor. What is its definition? Semiconductors added with foreign elements as impurities is known as extrinsic semiconductor. I repeat, semiconductor added with foreign elements as impurities is known as extrinsic semiconductor. Now what are its properties? First, number density of electrons is not equal to number density of holes. That is, Ne is not equal to NH. Either Ne is more than NH or Ne is less than NH. Second, conductivity. Conductivity is equal to Ne into E into mu E plus Ne into E into mu H. We take out E common. Ne mu E plus Ne into mu H, where Ne is number density of electrons, mu E is mobility of electrons, and NH is number density of holes, mu H is mobility of holes. Here we take out only E common and not N, because Ne is not equal to NH. In intrinsic semiconductor, Ne is equal to NH, so we take it as Ni. Assignment 14 continued. Question number 11. In an intrinsic semiconductor, the energy gap is 1.2 electron volt. Its hole mobility is much smaller than electron mobility and independent of temperature. What is the ratio between conductivity at 600 Kelvin and that at 300 Kelvin? Assume that the temperature dependence of electrons or hole or charge carriers is given by the expression Nt is equal to N0 into e raised to power minus Eg by kBt, where N0 is number density at 0 Kelvin, that is constant. So your answer should be about 1 into 10 raised to power 5. Question number 12. A semiconductor has electron hole concentration of 3.45 into 10 raised to power 22 per meter cube and 0.5 into 10 raised to power 20 per meter cube. Find its conductivity. Given mu E is equal to 0.135 meter square per volt per second and mu H is equal to 0.048 meter square per volt per second, and E is equal to 1.6 into 10 raised to power minus 19 coulomb. Okay, you solve these numericals on the basis of the text that you have learnt. Thank you so much. Next time we will take next part of it, doping. Till then, goodbye and good luck to you.